Okay, Chapter 8 is on exponentials and logarithms, and this video will start with a brief review of the properties of exponents. We'll do some graphing of growth and decay and transformations, and then do applications with exponential change, compound interest, and half-lives. So remember, multiplication is repeated addition. When you have 3 times 4, that means you're either adding 3 4 times or adding 4 3 times. In this case, we'll say it's adding 3 4 times. Exponenting is repeated multiplication. So 3 to the 4th is 3 times 3 times 3 times 3, which is 81. This is important to understand and just have in the back of your mind for this whole chapter. Everything we're doing with is multiplication when we're dealing with exponentials. Multiplication or division. So the graphs are different, the change is different, slope isn't a word that really applies anymore. And so with that, we've got to be able to work with the properties of exponents. 2 to the 3rd times 2 to the 5th becomes 2 to the 8th. The powers add, and 2 to the 8th is 256. So for the rest of these, see if you can simplify the following 7 problems before I go. Just, pause the video and think about them. This one in particular should give you some pause, and I bet this one you know how to do, but you kind of forget. This is 2 to the 3 plus x. The powers add. Here the powers add become 8. Here they add, so 3 plus x is 3 plus x. We can't simplify that any further. 256 we could calculate, but since there's a variable up here as a power, that can't go any further. This is 2 to the 1st, so it's 2 to the x plus 1. It is not 4 to the x. Those are very, very different. So don't think of that as 4 to the x. You can't multiply those bases. The rule is, if you have the same power, simplify the bases. If you have the same base, simplify the powers. So here we had the same base, so the power is 1 plus x added. Here we have the same powers, so the base will simplify. This would become 6 to the x. Remember, you could always just check this by plugging numbers into your calculator and plugging in like x equals 2 and seeing if they come out the same. This one here, think of it as 2 to the x divided by 2. 1/2 is really 2 to the negative 1, or it's you have a 2 on the bottom. So we're going to subtract these powers. It's 2 to the x minus 1. It definitely doesn't just become 1 to the x, because 1 to the x is just 1 for any value of x, so that's pretty silly. 3 times 2 to the x is already simplified. That can't go any further. 2 to the negative 3rd. A negative power flips a fraction, so 1 over 2 to the 3rd is 1 over 8. Negative powers flip fractions. This is the square root of 2 to the 3rd. Fraction powers are roots. The top number is your power, the bottom number is your decimal. So this is really the square root of 8, which we would call 2 root 2. When in doubt, expand it out means like if you're not sure what to do, write out 3 2s and 5 2s to get 8 2s, for example, up there. But that's your properties of exponents. Functions with the variable as a power are called exponential functions. When the variable up here is your power, things change. It's an exponential function. Because they involve repeated multiplication, they eventually grow or shrink very quickly. Much quicker than any polynomial over time. So some polynomials can grow faster to begin with, but exponentials will always end up growing or shrinking at a faster rate given enough period of time, a high enough value of x. So I'm going to graph y equals 2 to the x. I'm going to make a table, and in this table, plug in numbers from negative 3 to 3. If I plug in 0, 2 to the 0 is 1. Don't forget that. That's important. Anything to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3rd is 8. 2 to the negative 1 is a half. Negative 2 is a quarter. And negative 3 is 1/8. So this graph, and I'll give it a nice x-axis or y-axis here. I'm going to put the x-axis here. This graph is never going to go negative. In fact, it's never going to touch the x-axis at all. So here's an 1/8, here's a quarter, here's a half, 1, 2, 4, 8. This graph has what we call an asymptote. An asymptote is a line that your graph is continually approaching and never actually touching. I kind of missed this point up here, but we're going to live with that. This has an asymptote at the line y equals 0. Because no matter how negative I go, 4, 5, 6, these fractions will just keep getting smaller, but they never actually become 0, and they certainly never become negative. Over here on the other side, we're going to have 1/2 to the x. So I'll plug in the same numbers. If I plug in 0, I still get 1. I plug in 1, I get a half. I plug in 2, I get a quarter. 3 is an eighth. So this is going to go like this. That's supposed to be a half. It's a little high. Negative 1 flips this fraction over. So 1 half to the negative 1 is just 2. This becomes 4. This becomes 8. This graph has the same asymptote at y equals 0. When I graph that one way better. It just shows decay. If the base of your exponent is bigger than 1, you'll have growth. The graph will go up as you go to the right like the yellow graph does. But if the base is between 0 and 1, I can't just say less than 1 because it can't be negative. If your base is between 0 and 1, it has what's called decay. So this over here is growth, and this here is decay. Notice how these two graphs look like reflections of each other. Reflection over the line y equals x. I'll graph that, or sorry, the line of the y-axis. That's because 1 half to the x is really the same as 2 to the negative x. So here's 2 to the positive x, here's 2 to the negative x. The negative makes it reflect over the y-axis. So this is your basic growth and decay functions. In general, exponentials follow the AHK formula that we've seen with every other graph that we've done in this chapter, in this class, I'll say. A is your vertical dilation. If A is less than 0, then the graph reflects over the x-axis. It does the vertical stretching or compressing. B is your base. If B is greater than 1, the graph has growth. If B is between 0 and 1, the graph has decay. If B is 0, then it doesn't exist and it's all kind of pointless. If B is 1, then there's no change of any sort. So these aren't equal, it's just between. H is your horizontal translation. K is your vertical translation. And you have a horizontal asymptote at the line y equals k. So we're going to graph this function over here. I'm going to draw another set of x and y axes. It's good to have some idea of where this graph is going to go before I put down my full x and y axes. So by that what I mean is, I know this has an asymptote at positive 6. And I know that it's going to be going down like this. So let's think of this as 6, and this would be the x-axis. The graph is going down because of this, and it's zooming away from the asymptote because it technically has growth. We're going to call this negative growth that's going down. The point of this is to show I want to leave room at the top for this, but I want to give it lots of space to go down. These exponential graphs, notice I'm not using a rectangular grid. I'm using a fairly tall and narrow one, because they go up and down way more than they go left to right. So I'll make a table. I'll just plug in my negative 3s to 3s. Those numbers will work for just about anything we do in this chapter. In fact, negative 3 and 3 will usually be too big. And let's see how this looks. I'm going to delete all this. If I plug in 0, 2 to the 0 is 1, times negative 3 is negative 3 plus 6 is 3, so I have the point 0, 3. I'm going to count by 2s, so I should probably label that. This would be 2, 4, 6, negative 2, so I'm going to go negative 4, negative 6, negative 8, negative 10, negative 12, negative 14, negative 16, negative 18, negative 20, negative 24. Okay, so 0, 3. If I plug in a 1, I get negative 6 plus 6 is 0, so I have the point 1, 0. If I plug in a 2, it's 4. Negative 12 plus 6 is negative 6. And 3, 8. Negative 24 plus 6 is negative 18. So you can see, I mean, I counted by 2s, because I have a lot of ground to cover with that. In the opposite direction, though, negative 1.5 plus 6 is 4.5. So here's negative 1, 4.5. These are just going to keep getting closer and closer to 6. I think this is, okay, so negative 2, 5.75, 5.25. This is going to be something like 5.85. I'm not totally sure. It doesn't actually matter that much because the point is we just keep getting closer and closer to 6 without touching it. This is what I call negative growth. Growth means it's going away from the or away from the asymptote. As you go to the right, it zooms away from the asymptote, but in this case it's going down, so it's negative growth. So one more graph. Give the domain, range, equation of asymptote, etc. Again, notice how narrow this graph is because I don't really need a whole lot for this. It's going to go up and down really fast, but it's going to go left and right very little. This is decay, so the graph usually decays like this, but because it's negative, it gets reflected and decays like this, so it's actually getting bigger as it goes to the right, but it's approaching the asymptote with the asymptote at 4. Now, I could, again, more or less do this one by hand, but I think in this case I would prefer to just get precise points from my calculator because we need to be able to do both. So here's my graphing calculator. I'm just going to go to y equals, hopefully, turn it on. There we go. In the y equals menu, I have negative 3 times 0.2 to the x plus 4. I can graph it and see the graph. Here's the asymptote at 4. Here's the graph going left and right forever. But what I'm really concerned about here is the table. I'm just going to make a table that goes from negative 3 to 3. And then I can plot the points from this table real quick. So negative 3, 371 I can't fit. Negative 271 I think barely fit. So I think I'm just going to have this count by ones. Is that going to give me enough space? I think it's going to be close enough. So I have negative 1, negative 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Perfect. Negative 1, negative 11, 0, 1. Can I keep this on top? Nope. Negative 1, negative 11, 0, 1, 1, 3.4. Negative 1, negative 11, 0, 1, 1, 3.4. And the rest are just getting closer and closer to 4. There's the graph. Here's my x-axis. Here's my y-axis. And I should specify that I'm counting by ones. That's enough. Okay, the domain for all of these graphs is going to be all real numbers. X is in the set of all real numbers. The range for all of these graphs will always start or end at the asymptote. So y is going to be in the interval that goes, in this case, from negative infinity to 4. And it doesn't include 4, so it's got a parenthesis. The asymptote is the line y equals k, which in this case is 4. The x-intercept, I'm going to have to find on my calculator. I'm going to go to second trace and go to 0 and ask for the left bound. So I go to the left side of the x-intercept and press enter, and then right bound, go to the right side of the x-intercept and press enter. And it says guess, and I ignore that. This intercept is at negative 1.787. I'll just call it negative 1.8. The y-intercept we actually found precisely. You plug in a 0 for x, you get out 1. It's a comma. 0, comma, 1. This is what I call negative decay. It asks to identify the type of growth or decay. This is negative decay, meaning it's actually getting bigger, but the point is that we're constantly approaching this asymptote. Because this is a value less than 1, that makes it decay. So hopefully that refreshes you on how to do the graphing of these exponential functions. Now let's talk about some word problems, some applications. If something is growing, it's called appreciating. If it's shrinking or decreasing, it's called depreciating. Most commodities depreciate in value over time, like cars and motorcycles and food and television, those things. Some grow in value, though not always. Houses tend to grow in value. Gold and silver can go up and down, but overall tend to grow in value, as can some collectible items for a while, although rarely do these grow forever. Let's say that a car is worth $15,600 today, and depreciates or shrinks at a rate of 8.4% each year, what's the car worth in 10 years? Well, here is the formula we're going to follow for this. But the idea behind it is R is your interest rate, and 1 just stands for 100%. If something is shrinking at 8.4%, what that really means is you're keeping 91.6% of it. So the reason you do the 1 minus, or 1, in this case it's 1 minus because we're shrinking, it'd be plus if we were growing. We do 1 minus because if we're losing 8.4%, we're keeping 91.6%, and that's what we're talking about. The question is, how much do we have left? What's it worth? Not how much have we lost, what's it still worth? T is going to be time for 10 years. A is your starting amount, which is $15,600. And this is going to be the value of this car. Now, 8.6% is a pretty steep shrink rate, as you'll see. This value is going to just really plummet. Let's come over here. Wow, that thing moves real slowly. So I'm going to do 15,600 times 0.916 to the 10th. $6,487. So it fell pretty fast. That's depreciation. Had it been appreciation going up, we would have added. But it wasn't, so we didn't. 2 more. Compound interest is interest where people give you, well, interest in general is when people give you extra money or when you owe extra money based on some agreement that you have. There's 2 types, simple and compound. Simple interest is when the interest is only calculated based on the original investment. Its formula is also pretty simple, principal times rate times time. Compound interest is the one we'll be dealing with. It's when the interest is calculated based both on the initial investment, but also any interest that has been added as you go along. So let's say after a year you add some interest, then the next year there's more money in the account to add more interest. It keeps compounding on itself, and that gives you an exponential change. When you have compound interest, you're going to use this formula. P stands for your principal, your starting amount of money. R is your interest rate, written as a decimal. N is the number of times you compound in a year. That's the one that tends to cause people the most issue. And then T is just time in years. Let's do an example. So this account pays 5.4% interest, that's our R, compounded monthly. That means 12 times per year, so our N value is going to be 10 or 12. Our starting principal is $4,000, and our time is 15 years. So we have P, which is 4,000 times 1 plus 0.054 divided by 12 to the 12 times 10. Now, when this spits out an answer, a value, it's going to tell me how much total money is in the account in 15 years, not 15 months. People often think because we have this 12 here that we're dealing with months. What's happening is the agreement is we're getting 5.4% annual interest, meaning throughout the course of the year, we're going to get 5.4% interest. But because they're doing it monthly, they're going to split the payment up into 12 payments. So the 0.054 is broken up into 12 pieces, making the number here really quite small. But because it's happening monthly, it also happens 12 times as often, making the number here really quite large. So this gets small, this gets large, and those kind of cancel each other out a little bit, not fully. It turns out that if you compound more often, you will make more money over time, so we like having a higher compounding rate if the money is coming to us. But this result is going to be in the result of 10 years worth of compounding. 4,000 times 1 plus 0.054 divided by 12. In my calculator, I can just type this in exactly how I see it, except for I missed a 5. And then to the 12 times 10, or I'll just do 120. 6855.72. So we made about $1,800 in 10 years, which, isn't a ton of money. $2,800 in 10 years isn't a ton of money, but we also didn't do any work, which is pretty sweet. Finally, we'll do half-lives. Half-lives are radioactive materials that decay over time and release energy. And a half-life is the amount of time it takes for half of the material to vanish, to decay. So a half-life is a measure of time. It's a measure of how much time it takes for something to decay to half of its initial amount. Carbon-14 is a really common substance to use in half-lives because it appears in organic materials. So carbon dating is done with carbon-14 because of how it appears in organic materials. So let's say that an object starts with, that's the A value, starts with 48 grams of carbon-14. It has a half-life, this is our H from our formula here, it has a half-life of 5,730 years. And the amount of time that it's going to take is 10,000 years. The question is, how much do we have left after this period of time? Well, we can estimate this before we calculate it. If we think about it, 10,000 years is going to be almost 2 half-lives. Not completely 2 half-lives, but close, because 1 half-life is 5,730 years. So 2 half-lives is like 10,400 years. So this is going to be very, very close to 2 half-lives, but not quite. 1 half-life would be 24. 2 half-lives would be 12. So my guess is this would be like 14 or 15 grams. I'm going to do 48 times 0.5 to the... I have to do this in parentheses now. I'm going to close this because it looks prettier. To the, in parentheses, 10,000 divided by 5,730. I did 1,000, not 10,000. That's why it didn't look correct. This is why you estimate first, because you can see if your answer is wrong, because you have some idea of what it should have been before you finished. I was missing a 0, and now we get that 14.3. The half-life formula might kind of feel complicated, but it's really simple. You calculate here how many times half of the stuff is going away. Basically, how many half-lives are happening. To find how many half-lives, you take your total amount of time and divide it by the half-life itself. That tells you the number of half-lives. Well, then you do 0.5 to that power, and then multiply that by your starting amount. All of our formulas are essentially A times B to the X, right? Starting amount, some base, some power. They're essentially that. They can just get dressed up differently. Cap all this and shut it down. Y equals A times B to the X is the parent function of exponential growth and decay. If the base is bigger than 1, you grow. If the base is between 0 and 1, you decay. Exponential functions have horizontal asymptotes at Y equals K. And then appreciation, depreciation, compound interest, and half-lives all have formulas that are very, very similar to that parent function. Nice work. Boy, that was a long one. What's this guy thinking, making a video that takes like 6 hours to watch? And then now we get, again, distracted. Thanks for watching. I hope it wasn't too bad. Please like it, share it, subscribe to it, all those things. Tell your friends. Have a nice day.